Unit 8 is going to cover the gas laws, but before we get to the actual laws themselves, we need to talk about the units involved, and then we need to talk about in Section 2 something called the kinetic molecular theory. So we need to do those two things before we actually talk about the mathematical relationships of the gas laws. Okay, so the three major units that we're going to see with the gas laws are pressure, temperature, and volume. So we'll start with pressure. This is the one we're probably least familiar with of the three. It's a force exerted by a gas inside of a container upon the inner surface of the container. So, we're kind of at the point where some of you are starting to drive. You're familiar with, your tires needing air, and sometimes you'll get a low pressure sensor come on. Most tires need to be inflated to about 32 psi. And some are a little bit more than that, some are a little bit less, but that's kind of probably about where they average. And psi stands for pounds per square inch. So if you want to think of it as a square inch of space, okay, would need 32 pounds of force pushing against it from the inside, okay, towards the outside of that tire. So that's quite a bit of force in just a single square inch of area. But PSI is not a great unit for us to do science with. We need some metric units. So some more common units for pressure that we will see are pascals, atmospheres, millimeters of mercury, and torr. PSI, right, is kind of how some of the stuff's measured here in the United States. And bars we probably won't see unless you take a meteorology class. Okay, that's probably where you're most likely going to see that. The SI unit for this is actually the pascal, which is equivalent to 1 Newton per square meter. Square meter is, right, roughly 39 inches by 39 inches, which is way bigger than a square inch. And a Newton's not a really powerful force, at least for that amount of square area. So this is actually a very small unit. We don't typically measure things in pascals. Oftentimes it's kilopascals because this number is very small. The value of the unit's very tiny. Okay, so how did we actually come up with pressure? How did we measure it? At least the first recorded device of this came from an Italian guy, Evangelista Torricelli, who lived in the 1600s. You can kind of see a picture of what his device looks like over here. Okay, he's kind of got a large bowl, and inside of that bowl is filled with mercury, okay, which is a very dense liquid metal. And what he's holding here is a tall, narrow tube of glass with graduations in it, which you can kind of see over here in this picture. And he's filled that with mercury. He then inverts it and puts one end of it into the tub, and some of the mercury falls out, but some of it stays in the tub there, okay? And so what's going on? Well, the air, okay, from the atmosphere is pushing on the mercury in the tub, and consequently that is pushing up the mercury inside of the tube, all right? And so this thing was measured, or the graduations are in millimeters. It's filled with mercury. So he starts with this device standing at sea level, and he measures it that the mercury goes up 760 millimeters inside of this tube. That's how much force is pushing down on the tub of mercury, and that's how much is pushing up into the narrow tube. So that's how he's going to start. He's going to start at sea level. Well, as he kind of goes inland and the amount of air above him drops, okay, he's going to have less force pushing down on the tub, which is going to result in less force pushing up inside of the tube. So as he goes inland and his elevation goes up, okay, the amount of air pushing down on him goes down, right? It's kind of like the difference between Kansas City and Denver, Colorado, right? There's less air pressure in Denver, usually, because there's shorter distance between you and, well, outer space, right? So there's less air pushing down, which means there's less force pushing up the tube, and the level inside would drop. Now, this is not a perfect device, okay? He comes up with a unit here of millimeters of mercury, which we will see abbreviated mmHg. It's not a great unit, but it is a unit, and we were able to use it to actually start recording pressures of things. We knew air pressure existed, we just didn't have a convenient way to measure it before this. So this is going to start as millimeters of mercury. Later on, after he dies, this unit is going to also be called torr, T-O-R-R, in his honor. So, major conclusions from Torricelli. Number one, that air pressure at sea level is 760 millimeters of mercury. By the way, we are assuming this is an exact number, okay? So 760, right, with a whole bunch of significant figures, however you want to write it. Okay, we're assuming that that's an exact number. And secondly, that air pressure is going to decrease as elevation increases. There's less air pushing down on you, so that means there's less air pressure. So the other units come along later. After Torricelli dies, like I said, they also call millimeters of mercury torrs. So if you're standing at sea level, okay, we'll go ahead and make this note here, at sea level, okay, 760 millimeters of mercury is equal to 760 torr. They're the same, effectively the same numerical value, but just a different way of writing that unit. And so another thing that we did, scientists said, okay, well, let's just make the pressure at sea level 1 and everything else relative to that. And they called that unit 1 atmosphere. So if you're standing at sea level, yes, it's 760 millimeters of mercury. It is also 1 atmosphere of pressure. Those are the same value. These are a bunch of conversion factors here is what they are. If you convert that same value from millimeters of mercury into the unit of pascals, you get this really large number. I told you earlier the value of a pascal was very tiny, but 760 millimeters of mercury is 101,325 pascals, which is more commonly written as 101.325 kilopascals. Okay, we generally would write in kilopascals. It's easier than writing things in hundreds of thousands. But these are all the conversion factors for you to go between one unit and another. So make sure you've got these down here. All right, let's try this as a practice problem. The air pressure in Denver, Colorado is much less than that of sea level. It has a pressure of 626 millimeters of mercury. What is the pressure in atmospheres? So we're basically just going to do conversion factors like we did at the very beginning of the year. 626 millimeters of mercury. And our conversion factor here, well, we're going to get rid of millimeters of mercury, so it will go on the bottom. And the unit we're looking for is atmospheres, so it goes on the top. If you look at the previous slide, that conversion was 1 atmosphere for every 760 millimeters of mercury. So essentially all we're doing here is 626 divided by 760, and we'll write this to 3 significant figures because of this number. So this is 0.824 atmospheres, which I think is a really convenient way of looking at it, right? If you're standing at sea level, the pressure is 1 atmosphere. If you're standing at Denver, Colorado, which is roughly 1 mile above sea level, the pressure is 0.824 atmospheres. So you can see it's dropped 17.6%, okay, compared to sea level. So atmospheres are kind of a useful unit in that regard. Okay, go ahead and try these two. Remember, you're setting up them as conversion factors with the unit you're looking for on the top and the unit that you're starting with on the bottom, and the numbers that you are pulling from are from that slide 2 slides ago. Give them a try, we'll see how you do. Okay, so here are the solutions for that. This will give you 141 kilopascals to atmospheres. Well, we're setting that up with 1 atmosphere on the top, since that's the unit we're converting to, and the 101.325 kilopascals on the bottom. 3 significant figures because of the 141, so that's 1.39 atmospheres. Okay, and again, if you're not sure where these are coming from, it's coming from those conversion factors a couple slides ago. 325 torr to pascals, well, you're going to put pascals on the top, that's the 101.325, and the 760 torr on the bottom, that's the unit we started with. So it's going to be times 101.325 divided by 760. To 3 significant figures, it's 43,300. Okay, so we're pretty familiar now, hopefully, with pressure. We've been talking about temperature before in this class. Just as a reminder, the definition there, it's the measure of a substance's average kinetic energy, right? And that is the energy of motion, how fast something is moving, okay? Common units here, Fahrenheit, Celsius, and Kelvin. However, the one that we are going to put stuff in for this problem, for these problems coming up in section 3, is Kelvin. It's got to have a positive value. Celsius can be negative, and that's a problem. Here are the conversions for you. If you need them, go ahead and put them in your notes as well. Okay, converting negative 25 degrees Celsius to Kelvin. Well, Kelvin is equal to the degrees Celsius plus 273. So in this case, it's going to be negative 25 plus 273. So that's going to give us, let's see here, plus 273, that's 248. And notice when I say this, I'll say 248 Kelvin. I do not say 248 degrees Kelvin. Okay, we just say Kelvin, since it's an absolute scale. And of course, the last one here being volume. We should be familiar with this. The quantity of 3-dimensional space enclosed by some boundary. Common units are liter, cubic meter, cubic yard, right? So it's meters cubed, yards cubed, centimeters cubed, okay? And the one that we are going to be using most commonly is liters, okay? Assume that pretty much for all of our problems, liters is what we're going to be turning stuff into. There are some instances where we can use milliliters, but 1 liter is equal to 1,000 cubic centimeters, which is also 0.001 cubic meters. And that's all for the first section here. We were just talking about the units involved with gas laws and the conversions between some of them.